point Z here that I'm going to tell you is pretty cool. So let me talk about why that's really pretty cool. But first, I want to do a digression because geometry is awesome. This triangle right here, if we're assuming that this thing is a square, which I am assuming, then this triangle is the best triangle in all of mathematics. It's so cool. Why is this so cool? Because this is an isosceles right triangle. Sometimes you call it a 45, 45, 90 right triangle because you're thinking about the angles. But I want to say isosceles because these two sides are the same size because we're assuming that this thing is a square. And it is the best triangle in all of mathematics. So cool. In fact, there's more than one of these isosceles right triangles because here's another one. But if you look carefully, sort of like hidden pictures, you can find another isosceles right triangle in this picture. And in fact, look over here, there's another one. How do we know that this is also a 45, 45, 90, right? Because we know that our line of sight to this vanishing point has to be parallel to the orange line. That's what a vanishing point means. We know that our line of sight to this vanishing point has to be parallel to the edges of the cube, because that's what that vanishing point means. And we know that the front and the back of this cube are going to be parallel to the picture plane. So this is a 45, 45, 90 triangle. It's an isosceles right triangle, meaning this distance right here is the same as this distance right there. And that is so cool. And you're wondering, why am I saying that is so cool? And it's because, look, I just a couple seconds ago showed you this distance, which means we know this distance too. What is that distance I just showed you? It's this distance right here. It's something you can measure in the picture plane because that distance is in the picture plane. But this distance is out in the real world. What is this? This is saying if you're standing this distance away, but straight out from here. So now I wish I could do 3D like I'm standing. I don't know if you guys can see my camera, but here's me standing like in front of the picture about that distance. And if you can see my camera, you can. I'm going to just stop sharing for just a second just to make sure you can see. How do I do that? Does that? No, I'm afraid that if I do that, it'll kick me out of the meeting entirely. I don't want to do that. So, okay. So I'm just going to say, if you stand that close, it's really close. Like for an 8.5 by 11 picture, this is like 6 or 7 inches. That's much closer than you would want to see. And so I'm going to say, if you do that, if you get a chance to ever see that, this thing right down here, which looks like this weird oblong brick, actually starts to look like it's a square. So you're supposed to stand here and you're supposed to stand really close. There's a lot of clues that says you're supposed to stand over here. Notice that if you look anywhere above this point, you see the undersides of things, right? The underside of that shelf, the underside of that hat, the underside of this hourglass. If you look anywhere below this point, you see the tops of things. You see the top of the table, the top of the table, the tops of the bench. Likewise, if you look anywhere to the whatever this side is, left side of this point, you see the side that you think you ought to be seeing of those things, right? So this is saying you really should be standing over here, not in the middle like a tourist. And you should be standing much closer than is comfortable. Now, for you and me, when we looked at this beautiful picture by Durer, in the beginning, you were like, yeah, it looks fine to me. I don't get why Ivins was so unhappy. I mean, I guess he had to be because he was a museum critic and he knew what he was doing. You have to remember that Ivins wrote this book in the 1930s before cameras were ubiquitous. People didn't take pictures of everything everywhere. It was really hard. And so he was really accustomed to looking at the world, not through looking at photographs. He didn't have this sort of distorted sense that we do, that we're used to, of seeing small pictures of things that were taken in big places. So he really had a good eye for depth. He just didn't know the math to know that he should be right here. So that is, to me, a really good answer to this controversy. Durer knew exactly what he was doing mathematically. This is beautiful perspective. But psychologically, having people standing over to the side this close is really uncomfortable. People don't do that. And as a matter of fact, I've gotten to see some wonderful Durer images in the museum. And in order to get close enough to see it sort of pop into proper three-dimensional perspective, you have to stand so close that the guards get angry and tell you, could you please move back, ma'am? And you can ask me how I know that. So Durer made that a psychological mistake. If you're interested in learning more about this, there's a paper that somebody awesome wrote with my two friends, Fumiko Funimura and Mark France. in 2014, which we were doing for the 500-year anniversary of this totally awesome picture. So that's our first puzzle. Okay, here's our next puzzle. What the L, or pass the check, please. So I have my students draw pictures of words, and the word, oh, hang on, let me see if I can go find the controversy here. So Lamise drew a picture that looked like this. And she says, Dr. Crannell, this looks really awful. This is supposed to be an L, but this looks completely distorted right here. That does not look like 90 degrees. What did I do wrong? I did something mathematically wrong. What's going on here? And so the question is this thing supposed to be an image of a 90-degree angle, or isn't it? And how would we know? Because she was doing what I said of drawing two vanishing points and drawing lines going to the vanishing points and so on. So what's going on here? All right, so we're going to come back and say, let's assume that my student Kara is drawing a picture of a beach towel in two-point perspective. So two-point perspective means that there's two sets of lines that are not parallel to the picture plane, these lines that are parallel to each other but not parallel to the picture plane, and those lines that are parallel to each other but not parallel to the picture plane. So there's two vanishing points. Now, when Lamise finishes the picture, she puts the towel away, she turns it in, she goes away. So all I have is the picture. How do I know where I'm supposed to stand to make this look right? I don't want to recreate the Ivins mistake. I want to be in the right place. And the problem is I don't have the towel to help me out. Well, I could make some guesses. I could say, well, what if the towel were over here? If the towel were over here, then my line of sight to this vanishing point should be parallel to these two lines. Here's a line that's through the vanishing point, parallel to those lines. So I need to be standing somewhere on this line. And my line of sight to this vanishing point needs to be parallel to those two edges of the towel. So here's the line of sight that's parallel to those two edges. So I need to be on this line. So I need to be on this line and this line, which means I need to be here. But that's if the towel was oriented like this, because I don't know where the towel was. I only have the picture. So what's going on here? Maybe I could say, well, maybe the towel was oriented like this. Well, if the towel was oriented like this, then my line of sight to this vanishing point has to be parallel to these two lines. Here's the line of sight to the vanishing point that's parallel to those two lines. So I need to be somewhere on this line. But my line of sight to this vanishing point needs to be parallel to those two lines, because then my line of sight would never intersect those lines. So these two lines would appear to vanish. So I need to be somewhere over here instead, which is different than being over there. But maybe the towel wasn't in either of those two places. Maybe the towel was over here, in which case my line of sight to this vanishing point needs to be parallel to those lines. There we go. And my line of sight to this vanishing point needs to be parallel to those lines. There we go. So I'm over here. Or maybe my beach towel was in a different place entirely. And so my line of, right. So you can see that I can get a bunch of different points where I could be standing. And at each of these points, what happens is that my line of sight to the two vanishing points, my pairs of lines of sight form 90-degree angles because they're parallel to these guys, and those are 90-degree angles. You can also see it seems to be tracing out a curve. So in mathematics, it turns out that there is a fancy name for a curve that has this property. Maybe you even have heard of this before. It's a curve that has the property that anytime you're standing along the curve and you look at the two edges here of this curve, your line of sight to those 2 points is going to be 90 degrees. I don't know if anybody here thinks it has a name, that curve. Ready to guess? Ready to guess? It's a semicircle. Like when you guys were in geometry and you learned like, oh, if you inscribe a triangle inside a semicircle, you get a right triangle. That was a theorem that you learned that was like, why would I ever need to know that? Stupid thing to memorize. You need to know this because if you go to an art gallery and you see a painting in 2-point perspective, you can find the two vanishing points and you know to stand on essentially the hula hoop that goes between those two vanishing points. That is really cool. It'll allow things to pop into correct perspective. If you don't stand on that hula hoop, what happens is that you think, okay, my line of sight to this vanishing point has to be parallel to those two edges, and my line of sight to that vanishing point has to be parallel to those two edges. And what you'll see is something that looks really distorted, something that looks like it doesn't have a 90-degree angle. You'll see something that looks like this. Why does this look so bad to you? Because these two vanishing points are really close together. On my computer screen, they're about 7 inches apart right now. And I am definitely way further than 7 inches away. So this is why this looks distorted. If you want to, like maybe nobody's watching you right now and your camera's not on. So if you could do this, if you wanted to get your head really close one eye, that helps because looking out of one eye helps with perspective. Get your eye and basically like almost put your forehead, oh, sorry, I know it's getting really loud if I do that. Put your forehead almost on the computer screen between those two dots and look down at it and you go, oh my gosh, it looks like it's 90 degrees. And then you come back up, oh, now it's pointy. And then you get close, oh my gosh, it looks like it's 90 degrees. Anyway, that's so much fun to do. Where you stand really affects how something looks. It's not just, was the artist a technically competent artist? It's really about how you as a person stand in front of art. So that's my second puzzle. What the L? Yes, this is an L. Again, what Lamise did was technically correct. It's just that she had her vanishing points so close together that people aren't likely to be there. Now, professional artists know that if you want something to look realistic, they don't know why, but they know that you need to have your vanishing points being very far away. They say that's to minimize the distortion, but that's really to make it so that people who are standing far back are basically standing in the right place. Artists will actually often tape 2 pieces of paper that stick out on either side right here to the paper, and they'll put their vanishing points way far away to make something look more natural. Okay, so that's my second puzzle. Here's my third puzzle. When does a quadrangle look like a square? So what's a quadrangle? A quadrangle is something with 4 sides. I have 4 quadrangles here. They're all A, B, C, D. I've shaded them. My co-authors really hate that I shade them. They say it's not line segments, it's lines. You shouldn't shade them. I think if you don't shade them, it's really hard to see them. But this thing right here looks like it might be what you would think of as the perspective image of a square. If you're drawing a tiled courtyard, you might imagine that you would see things that look like this, right? These 2 things don't look like they could be images of squares that an artist would draw. And so the question that I have is, which of these things actually is the image of a square? And if like this is not and that's not, what makes the difference? Okay, so here's my colleagues saying, yeah, don't shade them. Grump, grump, grump. I think I need to shade them. The surprising answer actually is that all of these are the images of squares. And I'm going to show you this 2 ways. One is that I'm going to show you sort of a mathematical proof of this, zoom in through that. And then the next thing that I'm going to do is I'm going to actually show you like oh yes, it actually makes sense to a human being way of understanding that. So here's the big idea. If we have a quadrangle A, B, C, D, so here's a quadrangle that's a convex quadrangle right there. What we're going to do is do the same thing we did with the Lamise thing. We're going to find the vanishing points. So these 2 edges right here will intersect in a point called V. We can think of that as a vanishing point. These 2 points here intersect in a point V prime. So those are our 2 vanishing points. This means that this line right here is kind of like a horizon. And so we can draw the vanishing points of the diagonals. We saw in the Durer piece that it's sometimes nice to have the diagonals. The cool thing is if this is the example, if this is the image of a 90 degree, this is not a 90 degree angle, but if it's the image of a 90 degree angle, we know we're supposed to be somewhere on the semicircle between these 2 points. But if this is also supposed to be a 90 degree angle because this is the image of a square, then we're also supposed to be on the semicircle between those 2 points. So here's the semicircle between those 2 points, and there's the semicircle between those 2 points. So if we're supposed to be on this semicircle and that semicircle, obviously we're supposed to be sort of standing right here. And so that's going to be an important point for us. Now you could say, can you still do this for things that are not convex, for quadrangles that are not convex? Here's a quadrangle that's not convex. And you can say, yes, you can still find, here's a vanishing point V. That's the opposite side of these 2. Here, the vanishing point is sort of surprisingly in the middle. And the diagonals here actually, like the diagonal connects B and D and A and C. So the diagonals are on the outside of this weird bow tie thing. And so you can still find like, oh, okay, I'm supposed to be over here on the intersection of these two guys. So the construction that I gave you feels much weirder for a bow tie, but you can still geometrically do it. So, okay, so we've got this thing that's our quadrangle. And what I'm going to do is I'm going to find all those vanishing points. Here I am sort of thinking of this in 3D. And then we do the, I'm going to erect a little plane here and make a semicircles going through those planes. This is the point where I want to stand to make this thing look like a square. You could sort of think of like maybe putting your eyeball there. Maybe there's a candle there shining light. And in fact, if you shine light through these guys, it turns out you get a square. Exactly a square. So this thing is the image of a square, which is really cool. That's the geometrical way that you do this proof. Shooting these light rays. Now, this is supposed to evoke something that looks like it's three-dimensional, but I want to say, actually, it's not. It's on my computer screen. It's a two-dimensional thing. In this computer screen, the line from O to my vanishing point is like a line of sight to the vanishing point. It needs to be parallel to this, and you can see it is actually parallel to this. It's part of the way that we constructed O. And so you get this like Z thing that's happening right here. The Z is like a Zorro technique. This is how we're going to come back to the Zorro technique. Like you shoot something to the vanishing point, you shoot the line through your image to this thing called an axis, and then you shoot it back parallel to the original line, and that's going to give you the square that you need. And so this is a construction that can work on a plane. It doesn't have to be in 3D. You can just always do this cool Zorro thing and make squares. So we're going to come back to that later. Anyway, that proof was the way that mathematicians can prove that every single quadrangle that's out there is the image of a square. But you probably are still wondering, like, wait, how can a bow tie be the image of a square? It still doesn't make sense, even if it works mathematically. And so that's what I want to say. Like, how do these two things look like squares? And the answer is actually, unfortunately, my colleagues were right. I shaded this wrong. And it comes back to this thing that I told you before. The other weirder things can happen in math. So those are weird images of squares if you shade them differently. So here's what I want to say. This bow tie-like thing is the image of a square if you assume that your eye is right above the square. In some places, you're looking down at it like a shadow. In some places, it's shooting through like a camera. Remember how that weirder thing had like the triangle wrapping around? It's not the bow tie part that maps to the square. It's the outside of the bow tie thing that maps to the square. Or this like Captain Kirk logo, it's not the Captain Kirk logo that maps to the square. It's the outside of that Captain Kirk logo that maps to the square by sort of wrapping around infinity. This seems really strange, but you've actually seen this in your own real life occasionally. Let me pass through this. You've seen it like this. So here is a circle. There's a light inside this circle that's on the lampshade. And the image of this circle is actually a hyperbola. It's something that runs off to infinity this way. And if you could look at the other side of the hyperbola, it would be down here. This is a bigger hyperbola because this is the image of a bigger circle right there. But this hyperbola is the image of a circle. And so you're used to seeing something that looks convex like a circle have an image of something that's a really weird shape. This thing in the middle is kind of like the bow tie that we were talking about before. So in the same way, if you had a square lampshade and you looked at what the shadow, what the light pattern would be, you would have light up here from this, you'd have light down there, and in the middle, you'd have that Captain Kirk logo. That's why this square has an image that looks sort of like the outside of the Captain Kirk. Or you could have something that's tilted a little bit more like parallel to the picture plane, and you would have the light being out here. But in the middle, there's that bow tie. So that is kind of like why quadrangles act a little bit like hyperbolas and ellipses and circles. They're all kind of related to each other in those ways. In other words, when I said every quadrangle looks like a square, I shouldn't think of a quadrangle the way that I originally did it. I should really think of the quadrangles as looking like that. And then all of these things are images of squares if you put the squares in the right place. Okay, here's our 5th math puzzle. Why should you care? Like, maybe you're not going to be a curator in an art museum, or you're not going to draw things in 2-point perspective, or you're not going to do these weird math proofs about crazy quadrangles and shades. Well, the reason that you should care is the matrix, and in particular because when we actually draw pictures using computers, we use cool computer graphics. The way that we do this is we assume that every single thing on this light ray shooting out of our eyeball is the same point. So you can sort of think of these as vectors, but I want to think this vector, which is 1, 2, minus 2, is the same thing as 3, 6, minus 6, because you just multiply by 3, or you can multiply by 7, or you can multiply by -1. All of these vectors shooting out of my eyeball give you the same point. By saying that these are all kind of the same, we're using something called homogeneous coordinates. And we usually then take the random point that has the z equals 1 to say where we want to put it on the picture plane, because we think of this, the picture plane, as being z equals 1. So you've got these points on the picture plane that represents points, light rays in the real world. This is how we do things in computer graphics, and you move them around with a 3x3 matrix, which is really cool. So if you apply this weird 3x3 matrix to a set of really nice looking points, you get a really yucky picture. Can you deconstruct what was going on? Well, in the same way that every single quadrangle looks like a square, it also tells you that if you apply a matrix to every matrix applied to nice data will give you a nice picture, provided you look at it from the right place. I just had a yucky picture, but I'm going to say that yucky picture is going to look right if you look at it from the right place. So here's the details. Okay, you guys got all of this? This is, so you do your vanishing points. Here's your matrix. You find the circles that go between the vanishing points. You locate, this is the linear algebra for saying exactly what I just did with the pictures. Lovely. Oh, and a few more details. We find the place where you stand. And look, here's what happens. If I transform this around by standing here, you can see that if I put my eyeball here, this weird shape that I had before, which looks a little bit like a spaceship, transforms to this big house. In other words, the image of this thing is this house, which was this was my original nice looking data. So looking at this looks like the house. This is related to something that we call anamorphism, looking at something from a strange place. Here's one of everybody's favorite examples of anamorphism. This is a painting by Hans Holbein the Younger called The Ambassadors. And what he did was he painted these two wealthy French dudes, and he had this weird smear in the middle of this. And this weird smear was saying to these French dudes who had like the latest GPS system, the coolest music stereo system that they had, fancy like YouTube channels over here. But he said, dudes, you're all gonna die, because if you stand off to the side of this and you look down, you see this weird skull coming out. Anamorphism is so cool that it's not just Hans Holbein does it. Lots of even more modern artists do it. There's a sidewalk chalk artist named Julian Weber, and this is a weird, if you look at it from the wrong place, this is just a weird smear. This is a real kid. This is a real pole, but this is a drawing of a grasshopper, and the drawing of the grasshopper stands out weird like this unless you stand in exactly the right place in which it looks exactly like a grasshopper. This idea of standing in exactly the right place to make something look really cool in 3D is a famous example of something called anamorphism. And being able to understand computer graphics and stuff is going to help you figure that out. So that's cool. All right. I'm going to zoom through. Do I have 5 more minutes, or do you want me to stop?
Oh, sure. Five more minutes is fine.
Okay. Okay. I'm going to talk really fast, guys. Hang on. Imagine you have this weird detective question. Suppose you want to try to figure out what's happening from a photograph. Can we reconstruct the entire crime scene? So here's the crime scene. Suppose you had these two beautiful pictures on the wall, and then somebody stole the pictures, and you have to figure out which one of these two pictures was larger in the real world. Like, and you only have this photograph. Oh my gosh, now these are supposed to be two images because it's like an origami competition. So these are pictures of squares of things. How do we know which one was larger? We're going to go back to that Zorro thing that I told you about before. Because this Zorro thing says your line of sight to the vanishing point has to be parallel to the original square. These are like the images of those origami pieces. So to figure that out, what we do is, first of all, we find the vanishing points. Now, the vanishing points, there's two sets of vanishing points for the green lines, but if I do too many of it, just the lines go crazy. So there's one of the vanishing points for the green flyer, and there's the other one. The purple has a vanishing point here and here. So we know that those are the vanishing points, and then we do the circles through these. So imagine you've got a semicircle that goes through Vy and Vy prime and Vg and Vg prime right here. And the semicircles will intersect at this point O. So then you know your eyeball is supposed to go at O. Okay, so here's your eyeball at O, looking at those vanishing points. But remember, because of Zorro, your line of sight to the vanishing point is supposed to be parallel to the line in the real world. So we can just say, okay, let's go ahead, and this is all stuff you can draw exactly on the photograph. Like, you don't have to go into weird 3D things. You don't have to do matrix computations. You can draw all these lines right on your photograph right here. And by drawing those lines that head out in these directions, you can see, like, okay, the green square was closer. Here's the green square is closer. The purple square was further away. The purple square is further away. But you can also see this was the actual size of the green square, and that's the actual size of the purple square on the wall. If this is an 8-foot wall right there, that means that you can actually figure out exactly how big these were without actually doing, like, finding coordinates or anything, just drawing a bunch of lines and circles. So in fact, you could figure out if this is 8 foot high, then this yellow flyer was this, and by yellow I mean purple, sorry, was 24 inches, and this green one is 18 inches. So, all right. Let me skip through the advertisement because that's my book. Yay! That was the advertisement. And so here is what we've done today. We solved 6 problems. Did Durer draw a square? Yes, but only if you stand in the right place. Did Lamise draw an L? Yes, but only if you stand in the right place. When does a quadrangle look like a square? Always, but only if you stand in the right place. Why do we care? Because this helps us reconstruct, draw really amazing pictures of the real world, including pictures that fool people, but also it helps us to reconstruct photographs that we have in real life. And we're surrounded nowadays by photographs, so understanding how to analyze them is a really wonderful skill to be able to have. The summary of all this is that drawing a square isn't as easy as you think. Or maybe actually it is really easy because every single quadrangle is a square. But looking at a square, at a picture of a square, isn't as easy as you think. And yet, if you do know how to look correctly, there's really beautiful mathematics that you can find in perspective art. And here's some of that beautiful mathematics. Thank you very much.
Let's thank Dr. Crannell.
Woohoo! I'm imagining loud cheering.
Yeah. Yeah. That was so nice. Thank you so much. That was very great learning and very engaging too. And so, any questions for Dr. Crannell?
It's so hard to ask questions at a math talk normally, and then asking questions at a math talk via the computer is like extra degree of difficulty. So I will say, if you can remember my name, which is in the program, and you just Google me, you're not likely to get to any other Annalisa Crannell. It turns out there's really only one of me that I know of in the world. And you can find my email address. I would love to hear from you if you do have questions, if you want to play around with us. So, thanks.
I had one question. When you do you have a course in this at Franklin and Marshall?
Indeed, I do. It's called Perspective and Projective Geometry, which is related to the book that here, hang on, let me see. So sometimes I teach a first year course, which is like a freshman seminar, which does not use projective geometry, but it uses Euclidean geometry to draw pictures. So the student work that I showed you at the beginning came from this book, Viewpoints. But I also have a book, Intro to Proofs, that has this book, which is Perspective and Projective Geometry, and it's inquiry-based learning. So every single chapter starts out with a picture that's a puzzle, and students try to understand how to draw that puzzle, and then it goes into like, here's the math terms and here's the proofs that you do. So every single chapter has art assignments or photography assignments, which are actually harder than the drawing assignments, and proofs and short answer. So.
That sounds like would be a great course to take. And you say that is that a freshman course?
So the Intro to Proofs course is actually at the like sophomore level. We assume that I teach students to use LaTeX, and they're actually proving things. So in my institution, we have Calculus 3 as a prerequisite. Just for mathematical maturity, you need 0 calculus to do this. So the Viewpoints book is a good book for first year students that has no prerequisites at all. And the perspective geometry, let me see. Okay, good. I just unstopped sharing. This particular book really is a great book for students who are starting doing mathematics and really want to get into fun geometry puzzles, but also proving things.
Well, thank you so much. This has been such a great talk, and I really appreciate that.
And thank you so much for inviting me. I know I was supposed to be coming to Alabama last year to give a talk, and for some reason I decided not to go. Actually, decided to uninvite me last year. But I'm really glad
Sorry.
I'm really glad I got to come this year. And the trip to Alabama just keeps getting shorter and shorter. I just walked upstairs. So.
Yeah. Well, maybe one of these years we could have you here in person as well. So let's thank her one more time, and then we'll begin the graduate school sessions. So thank you.
Thank you.
Yeah.
Thanks. Yeah.